Okay, so today we're going to go over the moment of inertia equation for a uniform solid sphere. And to start, we can just begin with the equation in integral form, which says that I is equal to the integral of r squared dm. And as a reminder, what this equation says is that to find the moment of inertia of a body, you can go ahead and integrate a bunch of tiny little mass elements by the distance r that they are away from their rotation axis. So for example, if our axis is the z-axis, then our r distance in this integral is going to be this length right here, because that is a distance that our little mass element is away from the z-axis. So I'm going to go ahead and label this r sub z. And so the next step is to go in and replace this dm in terms of density and volume. So because it's a uniform solid sphere, we can write that density is equal to mass divided by volume, but we can also write that it's equal to dm by dv. So if you take any tiny mass element in the sphere and divide it by its associated tiny little volume, you're going to get the same density as if you divide the entire mass by the entire volume, since it's a uniform solid sphere, aka density is uniform throughout. So therefore we can go ahead and write that I is equal to the integral of rz squared, and then this will become rho dv. And so the next step is to think about what this dv element means. So it's a tiny little volume element. So if I come down here and redraw this element, we're going to get something that kind of looks or resembles this sort of shape. So this is a tiny little piece of a spherical shell that surrounds or is part of this sphere. And our goal is to think about these dimensions right here. So let's start with this one right here. As you can see, I've drawn 3 different coordinates. We have r, this distance of the mass element from the origin, theta, the angle from the z-axis, and phi, the angle from the x-axis. And so if we consider that this is a spherical shell piece, then hopefully it is becoming clear that these side lengths are actually little tiny arc lengths. So for example, this is a little tiny arc length that's rotated in theta, aka it's a distance r away and subtending a very tiny angle in theta. So by the arc length equation, we can write this as r d theta. And similarly for this little segment right here, this little segment, that is an angle in phi. So it's subtending a tiny angle d phi. And this time its distance is this length right here away from the z-axis. So with some trigonometry, if you notice that this is a right triangle, we get that we have this length as r sine theta. And that's just because our r is the hypotenuse and our length is the opposite side from theta. So we have r sine theta. And then we have d phi because it's subtending a tiny angle in phi. And notice that this is the same thing as r sub z. So we can go in and replace that in our original equation when we get the chance. So next we have to think about this segment, and this one's a little bit easier. That is just a little tiny change in the thickness of our spherical shell, or in other words, dr, a tiny change in the radius. So now that we have all of these dimensions, we can go ahead and think about what our dv element is. And it actually is just the product of all of them. So we end up getting r squared sine theta dr d theta d phi. And we can treat it as a product because these are infinitesimals, remember, each of these things, each of these little arc lengths. So because they're so small, we can treat them almost as straight lines, and then this weird little shape becomes pretty much a rectangular prism. And we get this volume here. So now we can go back into our equation and replace all of this. So this is going to be a triple integral now because we have 3 infinitesimals that we're integrating over. and I'm going to replace the r sub z with r sine theta like we had found. We still have rho, and then we have our density, or sorry, not density, our volume that we just found. So that's r squared sine theta dr d theta, d phi. And so our next step is to think about the bounds of integration, and that is a tricky part, because remember our goal in this integration is to integrate this sphere or form this body through integration. So there's a systematic way to do that in terms of these variables, and first it involves integrating in r, going from the origin up to our final radius r. So in a sense we kind of create a straight line. So those are our first bounds, 0 to r. Then with that line, we're going to rotate it around theta by pi radians, so that we're going to get this semicircle kind of thing as we fill it in, just like this. So we have 0 to pi in theta. And next, once we have this semicircle little shape here, our next step is to rotate it in phi by 2 pi radians all the way around the z-axis. And as that semicircle rotates, it's going to fill in a spherical shape. And that's how we get our final rotation to get our spherical shape. So we have 0 to 2 pi here for d phi. And so now we're all set to integrate. It's the only thing left we have to do. So first we can separate this integral. So we get that I is equal to the integral from 0 to 2 pi of d phi, integral 0 to pi sine cubed theta d theta, and then we have integral 0 to r of r to the 4th dr. And so the first and last integrals are not too hard to solve. We just get that I is equal to 2 pi from the first, and then our last integral is just going to integrate to the r to the 5th over 5. And then we still have integral 0 to pi of sine cubed theta d theta. And so now this integral we're going to go ahead and solve with a u sub. So we're going to let u, or before we do that actually, we should probably rewrite it so it's a little bit more clear. So we're going to get, and I forgot my density term also. So we're going to get density 2 pi r to the 5th over 5. And now I'm going to rewrite it as sine theta, sine squared theta. And I'm just going to go ahead and solve this integral right here. We're going to write it as integral 0 to pi of sine theta. And now using our trig identities, this will become 1 minus cosine squared theta d theta. Then we can go ahead and separate this integral 0 to pi sine theta d theta minus integral 0 to pi of sine theta cosine squared theta d theta. And so this integral is pretty simple. It just ends up being negative cosine theta from 0 to pi. And now this is where we're going to do our u sub. So we're going to let u be equal to cosine theta. And that means that our du is going to be negative sine theta. And so we're going to come in here and replace that. We sub in our bounds, cosine 0, cosine pi. And our sine theta is actually going to become a negative du, because we have a sine theta and our du is negative. And then our cosine squared becomes u squared. And now we're set to integrate this. So negative cosine pi minus negative cosine 0. Then bring this minus out, it's going to become a plus the integral from 1 to negative 1 of u squared du. Negative cosine of pi is positive 1, and then minus becomes a plus 1 plus u to the cube over 3, 1 to negative 1, which is going to equal 2 plus negative 1/3 minus 1/3, which is going to be equal to 4/3. And so if you remember, this was all part of this original expression. So now putting it all together, we get that I is equal to rho times 2 pi times r to the 5th over 5, and then times 4/3. And so you might think that we're done now or kind of stuck, but remember we can replace this density term in terms of mass and volume. So I is equal to mass divided by volume, 2 pi r to the 5th over 5, 4/3. And then the volume of a sphere is 4/3 pi radius cubed. And now you should start to see that things are going to begin to cancel out. So for starters, this 4/3 is going to cancel, pi is going to cancel, r to the cube is going to turn this into r squared. And now we are left with our final equation. I is equal to 2/5 m r squared.